This is my fully automatic LEGO chessboard. It's made of 100% authentic LEGO pieces, and it's a project that I've been working on for the past few months. It runs on EV3 MicroPython entirely locally, without an internet connection or dependency on a host computer. You can play against the computer, or it can even play against itself. This was a lot of fun for me to make, and I want to take you through my entire build process. Behold, the engineering design process. The engineering design process makes it easy to define and create a solution to a complex problem. The first and most important step of this process is problem identification, or the definition of the goal of the project. When I began this whole project, I had a few requirements for the chessboard to be a success. First, it has to be made from 100% authentic LEGO pieces. If it's made with non-LEGO parts or electronics, it removes part of the challenge and complexity of this project. It also has to be fairly cost efficient. I don't want to be spending an unholy amount of money on making this chessboard. So basically, the goal of the whole project is to make a cost-efficient, 100% LEGO, independent, automatic chessboard. The next step of the engineering design process is the research and brainstorming part. In this part of the process, you begin to generally define how you will achieve the different parts of the goal. For my chessboard, at a base level, I need a movement system that can grab a chess piece, move it to a new location, and let go of the chess piece. The simplest solution that jumped out to me was magnets. Magnets are the closest thing we have to actual magic, and having magnetic chess pieces would allow me to move them underneath the chessboard without being able to see what's actually moving them. Now, how would we grab and let go of these pieces? I had initially thought that the simplest solution would be an electromagnet. The electromagnet would simply activate underneath whatever piece it was moving, and then turn off once it had reached its desired location. Unfortunately for me, LEGO has never created an official electromagnet piece, so if I wanted to keep this project 100% authentic LEGO, I would have to come up with something different. The next idea I had was to just have another magnet underneath the chessboard that I could raise and lower. Raising the magnet under a chess piece would bring the magnets close enough to each other to have a strong attraction and to be able to move the piece around. When it was time to let go of the piece, simply lowering the magnet down away from the chess piece would let go. This seemed like a simple and efficient fix that I could flesh out later down the line in the design process. Now, for the movement system, I had initially written off trying to get this project to work because I had only considered using a Cartesian movement system to move the pieces around. A Cartesian motion system, commonly found in 3D printers or 2D pen plotters, uses two motors to independently control the X and the Y axis. My issue with this was the fact that for most of these systems, one of these motors, usually the X-axis, has to be situated on a moving belt, usually the Y-axis, as seen in this image of a 2D plotter. This specific plotter is from Superb Tech's YouTube channel. I have their video linked in the description. The LEGO motors and cables I'm using, which are part of the official LEGO EV3 kit, are big and bulky. Additionally, the LEGO cables are not very long, so having a cable attached to a heavy moving motor would be a very difficult system to try and replicate out of LEGO. And it would definitely take up a lot of space, taking away from a clean and polished look for the final project. I was stuck at this point for a little bit until I stumbled upon 3D Distributed's website breaking down a different type of motion system called Core XY. That website is linked down below as well. Core XY is also commonly found in 3D printers, but I had never taken the time to understand how simple it really was. It uses two stationary motors in tandem to move around the toolhead in the X and Y direction. It is somewhat of a difficult concept to wrap your head around, but this video by John Langseth is an easy way to try and get a grasp of how the movements of the different motors affect the moving toolhead. I realized that this motion system could likely be replicated out of LEGO fairly easily, and it solves the problem of the moving motors and short cables. Now the motors would be stationary and close to each other. The actual code for moving the pieces and playing the chess can be figured out later using the EV3, but for now, all the brainstorming is pretty much done. This brings us to the third step: detailing the best solutions and constructing a prototype. The construction of a prototype phase takes us into the final part of the process, which is the design feedback loop. Basically, you make a prototype, evaluate your solution, and redesign as necessary. This loop keeps repeating until you have a polished, finished project. For my prototyping, the vast majority of renditions were actually designed on a digital LEGO platform called Studio. I would make a digital design, order parts, wait for them to arrive, realize something doesn't work in real life the way it does on the digital design, and start the loop over again. I started off with the basic dimensions of the chessboard. The 8x8 grid of the actual chessboard itself is a 32 by 32 stud baseplate, which leaves 4 stud by 4 stud squares for each chess piece. The actual motion system, which takes up a lot more space than the playing area, is based on a 48 by 48 baseplate. I started out my first prototype on the blank 48 by 48 baseplate and came up with my first rendition of the Core XY motion base. Enormous shout out to this diagram from the official Core XY website. I copied this thing exactly into LEGO, and it was the best diagram around for understanding this concept. Once I had what I thought was a functional design completed in Studio, I ordered the parts and had my first working prototype. It was janky and slow, but it was promising enough to fuel me to finish the rest of the project. My next design challenge to tackle was the raising and lowering of the magnet. I went through many digital renditions of the system before I found a solution I was happy with. My initial idea was to use a newer LEGO Education motor and program the motor to raise and lower the magnet with either a linear actuator system or just a simple slider crank mechanism. This, unfortunately, introduces a lot of weight to the motion system. It would also require me to run a long enough cable to the motor and utilize a non-LEGO adapter to change the proprietary LEGO Education cable into an EV3 compatible connector. That would also mean my chessboard was no longer completely authentic LEGO, which would not align with one of our previously set out goals for the project. In my search for small linear actuators, I realized there is a much simpler solution the whole time: pneumatics. LEGO makes tons of different sizes of pneumatic pistons, and they have some small ones that ended up working perfectly for my needs. They're also super lightweight, and they don't need a bulky cable, just 2 flexible pneumatic tubes to raise and lower the pistons. They still require a separate motor to run a pneumatic pump, but I was able to build that outside of the chessboard shell. The need for a pneumatic pump actually brought me to an unexpected design challenge, but this design challenge was resolved almost magically. The LEGO EV3 only comes with 3 motors, and 2 of them were already in use for the chessboard. I needed to come up with a way to both run a pneumatic pump to build air pressure, and to also control a valve system to raise and lower the pistons, all while only using 1 motor. Miraculously, I was stuck on this problem for the whole of about 90 seconds when my YouTube recommendations blessed me with Serial's incredible design for a combined pump and valve system that only requires 1 motor. I have it linked down below. Huge props to Serial for making such an elegant and simple yet effective design. At this point, I had my motion system, I had my way to raise and lower a magnet, and now I just needed to find some magnets to tie it all together. LEGO used to make train magnets to link train cars together, and they work perfectly to make both chess pieces and the main magnet that moves them. Because of the somewhat bulky size of the magnet, I ended up designing a consistent sized base that is identical for all the chess pieces. When I came up with my first design for the pieces, I ordered enough parts to make the bases of only 4 chess pieces. It would allow me to test how they move and fit past each other. This is where I ran into an unexpected issue. With my current design, the pieces had no way of fitting between each other in the event of a diagonal move. This had me stumped for a while, and I had to make a tough decision. There was one other official LEGO magnet that could fix all my problems. It is a small magnet with a bar attached to it, barely larger than a 1x1. It would allow me to make much smaller chess pieces, completely eliminating the issue of collisions. The only problem? They only came in 1 set, 1 time, 20 years ago. This specific magnet was used in the 2005 Harry and the Hungarian Horntail set. As a result of this rarity, each one of those pieces cost about $20. Considering I need 34 to make a full chess set, that puts us at $640 for the magnets alone. If we factor in shipping, especially overseas, the magnet price would most likely reach over $1,000. Very few people have more than 1 of these for sale, so I would pay shipping probably close to 30 times. Even if this piece might be the solution to my problems, I'm not going to spend the value of a used car on some LEGO pieces. I ended up deciding to stick with my design, using the old train magnets, and I came up with an okay solution. I just have the magnet underneath the chessboard raise and lower on all pieces adjacent to a diagonal move to recenter each piece. I would rather spend 1/10 the price to make all the chess pieces and just deal with that small issue. At this point, I had a fully functional chessboard, in theory. I had a fast and accurate motion system, a functional grab and release mechanism, and compatible chess pieces. The last remaining part was the code for the whole thing. This is where reality struck my rookie Python skills. I had first thought that it would be fairly simple to take a pre-existing Python chess library and just import it to use it on the EV3. Guess what? The EV3 runs on MicroPython, and MicroPython cannot import any pre-existing chess libraries. Immediately, I hit what I thought was an impossible problem. I had been doing some of the earlier test code with the help of my dear friend Claude, and I genuinely thought that I would have to abandon the project or at least only make it work with limited functionality and not actually play chess. Then, Claude hit me with a question I didn't even know was possible. Claude rewrote chess from the ground up using MicroPython. From this point forward, all the code was written through days of vibe coding sessions, waiting for my usage to return, and slowly flushing out movement, quality of life, and general compatibility issues. In order for the chessboard to tell when I make my move, I needed to have a digital version of the real-life chess game running simultaneously. It took 19 renditions to get a version that I thought was acceptable, and finally, after all the reworks, I ended up with this. Here are some epic shots of different pieces moving and also some cool shots of the interior. It features a removable top and board for easy access to the internals. Like previously mentioned, when a piece moves diagonally, the magnet goes back along the path of the move and recenters the pieces adjacent to the diagonal move. The chess computer isn't very smart. It just kind of moves pieces randomly until it can capture a piece. And I tried to make it be able to think 2 or 3 moves ahead, but the potato of a computer that is the EV3 would take about 3 minutes to make each move, so I opted for a dumber but quicker approach. For taking pieces and castling, I unfortunately had to opt for human intervention. As much as I wanted every action to be completed by the chessboard, it would require a rework of the whole board to add that compatibility. The mechanics of the interior of this chessboard just barely fit. While the playing space is 32 by 32 studs, the actual movable space for the magnet on the inside is exactly 30 by 30, so the magnet couldn't even reach the edge of the board if it wanted to. I personally prefer to have a smaller, cleaner look and just intervene every once in a while. I thoroughly enjoyed the entire process of designing this chessboard, and I hope to display it at conventions over the next couple months. I really hope that this will look good enough on a resume to help me secure an elusive engineering internship. Thank you so much if you made it all the way through this video. This is my first time making a video like this, but I genuinely had a lot of fun doing it, so I might make more in the future. Thanks for watching. Toodles.